Hello everyone, my name's James Rowland Jones. I'm a Principal PM for Microsoft in the Elastic Scale team, which is a team that covers SQL Data Warehouse, the on-premise analytics platform system, technologies that you might have heard of in SQL 2016 like Stretch Database and Polybase, and then also some of the Elastic Query tools and APIs that sit as well a part of the team. Many people know me as JRJ. If you have any questions, either before or after, I conveniently have my alias as jrj@microsoft.com. More than happy to take questions both in the session and afterwards if needed. Okay, so what we're going to be talking about today is Azure SQL Data Warehouse, which is a service that is currently in preview. It's one of the fastest growing services that Azure has ever seen, and is getting incredible popularity and traction with a wide range of customers. Now, why do I say that? It's because it's not just about traditional data warehousing. What this is about scale-out analytical compute and being able to leverage set-based aggregations, set-based transformations using a distributed system. Okay, so that's what we're going to be talking about. If you thought you were coming in to see Mr. Woody or any of the other speakers, then you are more than welcome to go and see them, but that's not what I'll be talking about. Okay, so this is what we're going to cover in our session. A little bit about the underlying technology. I'll cover some of the partners that exist and kind of where we sit in the ecosystem. Some workload scenarios, and then finally some things about sizing. And if we've got time, I will also drop and sort of show you some demo stuff if we've got, if time permits. So let's start with the technology. The technology that sits behind us is designed for analytical workloads. I hope by now we can all separate the difference between a transactional system, right, and an analytical system. Unfortunately, many companies would term it as an OLAP database, right? Unfortunately, that term in world of Microsoft kind of sits very much in the world of analysis services as a semantic engine. But it is an analytical database. It's designed for you to do set-based aggregations, set-based transformations on data. Queries tend to be deeper queries across millions and billions of rows. But there's some other reasons why you might want to use a scale-out system. Some of those might include things like being able to consolidate your disparate data into a single location. One of the things that may be quite popular is that, I was speaking to a customer only yesterday, and they said that they have data warehouse, or a data mart. Their data warehouse is really a collection of marts, and they have them all on different servers. There's a lot of good reasons why that might evolve. It could be third-party products that have their own data warehouse components, all sorts of things. But then the problem always comes when you then need to be able to bring that data together to be able to form a single holistic view. Other scenarios that might have caused that to occur might be very simply that the data warehouse that they had just wouldn't fit on a single scale-up system, and so they actually split the data into different subsets and hold those out. The problem with that scenario is that then when someone asks for the global or the all group level reporting, they're either having to pull the data from a number of different locations to bring it together, or they are having to create another warehouse that holds the group level data. So neither of those are very exciting from a data warehouse point of view when you could simply do all of that type of analysis with a join. Other things is very typical in the new world of data analytics is that ability to be able to bring all the data together to be able to get new insights. If you don't have the data in a single location, that is actually very problematic, and that's something that big data addresses with a data lake. But this is something that we've been doing with data warehousing for a long time. Is this concept of being able to bring data together. Okay? Now, I tend to look at all of these sorts of things, but one of the main things for me is the fact that at the end of the day, what we're dealing with is a relational database management system that is a scale-out system, and we use SQL as our main language construct because the number of people that are able to use SQL is very high, ridiculously high, and you think about the number of people that know SQL compared to the number of people that know MDX or DAX, you immediately appreciate the value of SQL as a pervasive language. So much so that if you go back and look into the big data world, one of the things that you'll realize is that they've gone through their own little realization of this as they've gone through the no SQL to qualify to not only SQL to actually, that SQL stuff is actually quite useful to actually, I tell you what we really need. We need some SQL, right? So, and so you now have Spark on SQL and all these sorts of things that are materializing. So I have a general rule that is, if I'm going to try and do SQL, I'm going to do it on SQL. So I have this is my new little meme, which is SQL on SQL, and that's what we're going to try and do with SQL Data Warehouse, is enable people to leverage all of the rich functionality that's in a relational database management system that goes far beyond just the basic scaling of holding data in tables, but it includes things like sessions, concurrency management, security on data, all of those things that form part of it that we just take for granted. Well, in the big data world, all of that stuff has to be coded. If you want it, you've got to code it, right? So this is where I think the relational database engines still have an enormously relevant role in the world of big data and analytics. And so I encourage you to look at those. Now, what I would say is, though, that when you use a database that is targeted for a certain workload, you're also saying at the same time that not everything kind of fits in your space. And so sometimes it's actually valuable to be able to say what isn't applicable, right? And in our case, things like operational workloads, things where you have high frequency reads and writes, you know, where it's very pinpoint singleton insert, singleton selects, that's not really what we're all about, right? And so I would encourage you to kind of think about the kind of workload that you're trying to use and go for like the best fit service for that job. If you were trying to do something like that, you'd be much better off using Azure SQL Database, which has got a very high concurrency capability, can handle very high volumes of very singleton pinpoint inserts and lookups, and use that engine for that process. The other thing that we don't really do is what I would class as data preparation. Okay? Now, data preparation sits in the space of things like row-by-row processing. For those of you who've ever used integration services, the time to really crack out the data flow pipeline is that moment where you need to be able to actually build a position on a row, like an incremental position on a row before you release facts. That sort of thing is not really suited to set-based operations, right? Because typically you have to do that with a cursor, and cursors are not necessarily the most pleasant of things at the best of times. In a distributed system, they're really not very efficient at all. So we tend not to kind of want to see like row-by-row based data processing in the system. And the other thing is that we don't support, we basically ingest and support square data is the way I would describe it. Tabulated, delimited text data, as well as Hadoop file formats such as ORC and record columnar file and Parquet. But what we don't support are things like JSON and XML, okay? So those sorts of things, you would need to have some kind of pre-processing on the data. And for that, you may well use something like an HD Insight or an Azure Data Lake Analytics type process to be able to transform the data and essentially transpose it into something that was delimited and square. Okay? Does that all make sense, hopefully? So as a logical overview of what we're doing and what the SQL data warehouse is and why it is kind of interesting in some ways special is the fact that we start with a chunk of storage. And in that chunk of storage, we're using premium storage. Under the hood, we're running a distributed set of databases to hold your data. Okay? But what we do is we apply compute as a second and separate surface to that. Okay? Now that compute is broken up into two sections, a control node and compute layer. Okay? The control node is the guy that you connect to and the person that you submit your requests to, and he then breaks that down. He then breaks that query down and fires it against the storage layer. So the way to think about this, one of the first places I ever delivered any training on this technology happened to be in Chicago, which is a great place to talk about scale-out systems, funny enough, because Chicago has one thing in common with scale-out systems, and that just happens to be the mafia, right? So if you think about the way the mafia works, right, you have a mafia don, and he is the brains of the organization, and he comes up with the plan, right? And then he communicates his plan to his henchman, right, his protection racket, and he says, you go out and do all the work, and then you return back to me all of my money, right? So so if the mafia are in the world of building out database systems, they would clearly prefer to be using a scale-out distributed system or an MPP data warehouse, right? Massively parallel processing. Now, what I would say is interesting about our service is that we're able to then increase the amount of compute irrespective of the storage, right? We enable you to scale the compute both up, down, and also turn it off completely. Why? Because the compute is the thing that actually costs them money, right? In real terms, compute is about 9 to 1 in terms of cost, right? So actually being able to closely manage your compute is incredibly valuable. And we enable you to do this very, very quickly, very, very effectively. So we can provision in about 5 minutes, and we can scale from the smallest to the largest in about 75 seconds. Okay? And we can pause again in about 5 minutes, because now we've just taken all the compute away. There is nothing to attach to. Okay? But happily, you'll be pleased to know we also let you bring it back online again, right? Nice and quick. So you can optimize essentially your processing patterns around this concept. Vincent, you had a question.
Yeah, so you say you can scale the computer irrespective of the storage.
Yeah.
Does that mean that I could have a very, very limited amount of storage and by accident put in 200 compute nodes and have a load of compute nodes sitting idle because the storage is completely saturated, or it can't spit out any more data than the compute can take?
So the way we think about it like this, right? What we have is essentially 60 distributed databases, okay? And that, as an architectural point, is fixed in the service. It's just a number we've settled on for now, and we monitor that, okay? On top of that, we're then essentially mapping those databases into essentially like virtual machines is the easiest way to think about it. So you can think about it like a giant set of attached DBs and detached DBs, okay? And when you set your scaling, you are determining what the ratio is between those two things, okay? So the scenarios are we manage a lot of resource management to make sure that each request gets an appropriate amount of resources, okay? So, but what we do is enable you to scale that so that you can increase the amount of resources available. So, to Finton's point, what we enable is something called a compute scaling, and this is essentially this mapping exercise. So I like to use these are our SQL databases, and you notice that I have them shaped like buckets, okay, or pint glasses. because the whole point of MPP is like going with your friends to the pub, right, which I hope none of you will be doing at 2 o'clock today, right, to watch a certain game that may or may not be happening, and basically playing drinking games, right? So normally when I do this, I give everybody a pint glass and we fill them up with water, right? And I get you to each drink a pint of water, and at the same time I count up the number of students, and then I will try and drink the same equivalent amount of water, right? Because I'm a scale-up system and you would be the scale-out system. And I can guarantee you're done in seconds, right? And I'm dying of some form of water poisoning here at the end, right, as I've drunk about 4, 5, 6, 7, 10 pints of water, whatever it is. The point is that these buckets are kind of bottomless. You can hold very large quantities of data in here. We actually set the cap at the moment at 240 terabytes, compressed data. Okay, so across all the buckets today. So we set it at that, so it's roughly, it equates to, depending on your columnar compression, at about anything up to a petabyte capacity, right, because it's compressed, so the raw data capacity. But what you're doing is essentially changing the mapping as you increase the scale. Okay, so we increase this, and we're just changing that mapping as we go. So as you increase the amount of compute, what you're doing is increasing the ratio, or sorry, decreasing the ratio between compute and storage. Okay? And everything that we do under the hood is to affinitize your queries to those compute levels. And as I said to you before, we then enable you to pause the service to take that compute mapping offline so that you can then optimize your spend. Now, if you think about data warehouses, you might have a data warehouse that just feeds MOLAP cubes, or you might have a data warehouse that just feeds data marts that are then compute, right? So if you think about those scenarios, your data warehouse online today may be somewhat either very lightly used during the day once the data has been processed, or may actually not receive ad hoc queries at all. Okay? In which case, you have a very different, you have an opportunity to massively optimize your spend and consumption, right? You compare that to someone like on-premise, you think about your buying pattern when you're on-premise, you'll buy a SQL server, you have to buy the SQL server for the maximum scale you think you're going to need, you license all of the cores, and then you leave that baby on for the next 3 years, right? And that's your scale. So you scale to the maximum, you pay for the maximum, you pay for all the cores for all of the time. In this is much more of an OpEx model, right? This is CapEx versus OpEx. So this is an OpEx model where you're able to control that price point, okay? So for 2 hours of the day, you could be fully spinal tapped, cranked it all up to 11, right? Do all your ETL, then scale it right back to 100 for light level query during the day, or even turn it off, and now you have a completely different cost model to the one that you had before, right? And as I say, of course, we then enable you to bring that compute back online in a matter of minutes. All right? So this is the way that the query works, and I'll show you a simple example in a second to kind of help deliver the concept. So in comes the query. The query hits the brain, and the brain asks, or the control node, some fundamental questions, right? First thing is this person authorized for the request that they have submitted, right? It's a select. Do they have read access to the table? And if they do, we move to the next step, which is the person a Muppet, i.e. is the SQL syntactically valid? So we go through all of the standard processes that you would expect. But then we go through one extra process. We go through what we call the parallelization process, right? The MPP process, with scale-out process. And we work out a plan we call an MPP plan, okay, which basically breaks up your query into lots of queries and lots of little queries, and then we fire those down against the nodes. Once the nodes then process the data, they then return their results back to the user and for further processing. Now, what can happen, because the data is distributed, some things mean that we have to do things in what we call steps. Okay? There's not just a simple one-step answer. So the simple way to think about this is in the form of a count, right? A count is a very simple way to do this. So think about your count request. Now, if you fire a count at a SQL server, it's just going to count all the rows in the table, right? Happy days, and you get an answer. You don't have to think about it. But in a control and compute separated thing where all your data is spread across 60 databases, right, we actually have to break that down into steps. So the first thing we do is fire a count down at every single one of the databases to generate us a subtotal. Okay? So now, if I've got 60 little databases, I now have 60 subtotals, which therefore, they return their data, and they actually store it in a temporary table up here in the control node, right? And the control node has now a temporary table with 60 rows in it, so I fire a sum at that temporary table to calculate the final total, because what you asked for was a count, and then I return the result back to the user, which is the grand total, okay? Because we're not forcing you to change your query. What we're doing is making that transparent in the same way that SQL, you don't specify to SQL how you want the data to be accessed in an ideal world, right? It's supposed to do all that for you. It works the plan out. What you do is you specify the intent. That's the point of a declarative language like SQL, is you just say to it, what is the answer to this question? And you just get an answer. So everything about this is transparent to you. Now, how does the data land in the different tables, right? How does it get spread around the system? Well, we have two methods today of doing this. The first one we call the round robin. And the round robin is, I'll show you in a second, is the default, and it is a simple way of spreading the data as evenly, but with no optimization elements to it, around those 60 databases. The second method is a hash distribution, okay? A hash distribution, we pick one column in the table, right? In this case, you can see I've picked product, or item, and then basically we hash the data type of that column. And notice I'm saying data type, I'm not saying value, right? We hash the data type, right? So that when the values pass through, we are then allocating those rows based off that hash to a specific bucket. So let's look at it in the terms of the shape of our buckets on the round robin. Imagine I'm going to fire an insert at the table. What we do is we pick a bucket at random, and we fill forward from there for the duration of that insert statement. Okay? So then when the second insert comes in, he goes and fills in from that location, and so on and so forth. Okay? And we keep doing this for all of the inserts that happen. And so ultimately what you end up with is a very even spread of the data across all 60 databases. Now, that's a very simple way of doing it, but as I say, we generally aspire for better than that. But if it's a small table like a dimension, small dimensions, typically you'll see them use this round robin approach. Now the second way we do is this hash distribution, and the hash, let's imagine we are looking at a retail sales table and we've hashed by product. So the hash is this item here, the value here is the product ID 1. We hash it based on the type, and the data lands in a bucket. Okay, everyone happy with that? So when I see the next value, we hash that one, he goes in there, and the next value, he goes in there. However, when I see that product ID 1 again, the result of the hash is deterministic, and so he always lands in the same bucket. Okay? Now, once we have that level of knowledge in the system that we know that the hash is deterministic, we can start to make optimization assumptions about the way the data has been distributed. Okay? So let's think about that in the terms of a join and why that therefore this might be useful. Imagine we have a business that is a retail business that has a legacy bricks and mortar sales table, and then they have gone and invested in the interwebs, and so have decided to create a separate transaction for their web sales. Okay? So in the store sales table, we're both distributed by product key in both places. Now, if the product key is integer in both cases, then the data in both tables against both sets of buckets will be what we call co-located, i.e., all of the product IDs that were product ID 1 are in here, and they are also product ID 1, they're also in here. Bear in mind, the name of the column is utterly irrelevant. Okay? Utterly irrelevant. Okay? It's the type that matters for the distribution of the data. What matters is that when we join these two tables together and we include the distribution key in the join, there is no need to move data around the system in order to be able to satisfy the query. Okay? Bear in mind that these things are fundamentally like databases on the bottom end. And one of the things that you make an assumption about when you create a database on an SMP system is that the data is co-located, right? It's all in the one system, yeah? So when you do a join, that join happens in memory. You're completely assuming, yeah, that that is all taken care of for you. In a distributed system, that your data could be in some other location. So optimizing to make sure it's in the same location is actually really important. Now, let's go back to our scenario of this bricks and mortar business. Now, let's imagine a situation where a customer has a bricks and mortar business and they thought integer would be fine, but when they went to the interwebs, they decided they might increase the data type because they might want to dramatically increase the number of products that they had available, right? So let's just say they changed that from an integer to a big int. What do we think is going to happen? Well, let me show you. The distribution of the data will fundamentally change because the hash of a big int has to cover the full range of that data type. And so the data is now spread in a different pattern to the one on the left, or my left anyway. So the problem here is now that product ID 1 that was over here could now be down over here. So in order to be able to do the join, we would first need to redistribute one of the tables to make the types compatible so that the join would occur and happen in memory.
When you say redistribute, are you
Yeah.
talking about something similar to the old PDW?
Yeah, it's exactly the same.
Shuffle?
Yeah, in this case, we would shuffle. Yeah.
And we talked about the co-location of
Data.
tables for joining.
Yeah.
I mean, obviously, fact table is going to be much larger than a dimension table.
Yep.
So I'm just wondering how you get co-location with a dimension table and a fact table.
Well, so what we would do is for something like a dimension, which was round robin typically is going to trigger data movement generally, right? So what we would do is we would actually redistribute to an all. We'd do what's a broadcast, right? So if you know that the PDW movements, you'd use a broadcast. That would then push the data into every single node, so that then you would join across. Yeah, so that's how you do it. So under the hood, we're using the same cost-based optimizer as PDW, right? So the engine that drives the plans is exactly the same. So let me just step into that a second. So the shuffle, so what Chris is asking is, how do I actually resolve this, right? Now, we have lots of different ways, lots of different techniques for moving the data around, okay? Now, the important thing to you as the end user is that this happens automatically, right? But these all happen based on a cost-based optimizer that we have that's generating that MPP plan at the top, right? So what he's going to do is he's going to work out the best way to efficiently work out this plan. So what he's going to do is it will say, for example, in this case, if I try to join these two tables together, I have typing compatibility between these two tables on the join. So I have to effectively redistribute one table to make it compatible with the other table. And I need to do that so that it's type consistent. Okay? So what it will do is it will pick one of the columns that's used in the join, and it will use the statistical distribution of data, right? The statistics that we hold on those columns that you're kindly going to have created for us, right? It's going to use those to be able to work out which is the most efficient column to redistribute the data by, right? Now, in this case, because one of the tables is already distributed by a given column, that kind of already gives you most of the clues that you need, right? Now, we have lots of different ways of doing this. One of the ones that Chris mentioned was called the shuffle. It's actually one of the most common. So let me explain what that would be like, okay? And think of it, it's called a shuffle because it is like literally shuffling a deck of cards, right? Basically, we just redistribute the data that we require, right, by shuffling that data between the nodes into temporary tables to enable you to affect the join, okay? Now, when we do that, okay, that's going to add time to your query, okay? So by actually optimizing your data types, by looking for incompatibilities that might have crept in over time, okay? This is just one way of doing it, right? This is make certain assumptions, but it's a good way to start. It certainly beats trying to do it by just looking at code by hand across thousands of tables. What you're doing is planning kind of to minimize data movement. One of the things that I would say as an MPP person, one of the primary goals is to minimize unnecessary movement within the system. And so when you're tuning the system, this is one of the things that you'll do. Now, this code here, all it's doing is it's joining on the column name, so it assumes that the column names are the same, but it looks for differences in their type, their nullability, and things like that. Because one of the things that happens with data warehouses is they can be around for a very long time, so little inconsistencies can creep in over time. So it's always a good thing to step back through and reevaluate that. My point here is this. In a SQL server, this stuff all has a cost, but it's a cost that is largely something that you don't see. If you're very deep into query plans, you'll know that SQL Server, if it sees type inconsistency, it will do an implicit cast in the query plan to be able to do that, and there is a CPU cost to that, right? But it's something that is so well hidden in the ecosystem that most people don't even realize it's happening, or the query is fast enough and they don't care. In a distributed system, these things do tend to matter more, okay? And so it's something that is worth investing some time in. Chris, did you have a question?
No, it was answered.
Okay. Now, when it comes to loading data, we can have two ways of loading data. The first way is what we call the single-gated client. And you can think of things like BCP and integration services as ways of doing this. The analogy I'll give you is that of a house party, which when I'm away from home or when my wife and I travel, this is what invariably happens at my house because I have teenage kids who still haven't worked out that if all the pictures are slightly off, that something has happened in the house. When you return, it's very obvious that a house party has occurred, right? Now, what it is a house has a front door, right? And we think of the control node essentially like the front door of your house. So when you connect a client like an integration services destination adapter to SQL Data Warehouse, you're entering data through the front door. Now, very common pattern with integration services is the manual parallelization of data loading, okay? Which is a bit like running a house party and welcoming guests at the front door. You can only get them in the house as fast as you can get them through the front door, okay? Now, if your house was optimized for house parties, what you would have is a lot more doors, right? Because that way you'd get more people in your house more quickly. Thankfully, my kids haven't worked on that. Otherwise, I'd have many, many holes in the side of my house. Now, what we have, therefore, is what I consider like the back door, which is Polybase. Polybase is a way of interacting directly with the control node, with the compute nodes when you're loading data from blob storage. And what you get is a much more parallelized access. Now, hopefully, as you said, when I said you couldn't scale the compute, what this means is that as you scale the compute layer and add more nodes, what's going to happen? Load data faster, okay? And we can get up to many terabytes an hour of data loading capability by increasing our levels of scale. Okay? So rather than trying to push everything through and then fan out at the back, right? That's like a bottleneck, right? Okay? This is direct connections off the back. Now, SQL Data Warehouse is a fully managed platform as a service. Okay? So that means that obviously we're handling things like upgrades and patches, but also things like features, things like that. And we're releasing features to you all the time. The most recent one we just put in was AAD authentication. We added that into the service just very recently. And we'll continue to keep iterating that as we go through both GA and beyond, right? It's one of the most exciting things is that, you know, even with the acceleration of the box product to what's now, what, 2 months, every 2 years or so, we're shipping features almost like on a monthly basis, right? And that's very exciting. And there are things that, you know, some of the things that I can see in our roadmap are things that, you know, you won't see them anywhere else, but you'll see them first in this cloud-first, mobile-first world in the SQL Data Warehouse. So it's a great platform to be on from that perspective. Now, we enable a whole bunch of additional value-add properties through here as well, like audit and threat detection. Transparent data encryption is literally just a click away from you being able to kind of enable those things. And we'll look to add other things as we go. And I would encourage you all to, as you go through and explore the service, to post your feedback on the user voice thing. And I've got some links for you at the end. The reason I would say to do that is because I'm a PM on that team. We look at that, right? And we look at that very intently when we are picking features. And if you look at our user voice feature list, I can tell you that the things that bubble to the top are the things that the team are working on, right? So it's a very healthy thing to get into the pattern of doing, and it certainly helps us, and hopefully helps bring features that you want to see to the platform sooner. Now, one of the things that you are able to do when you're in the cloud that's a lot harder to do on-premise is things like geo-disaster recovery. So at this point, I'd just like to say, how many people here have a data warehouse or access data warehouses in their day-to-day environments? OK, that's most of you. How many of those data warehouses have site-wide disaster recovery attached to them? Okay, so we've gone from, say, maybe 20 of you to 2 of you have site-wide disaster recovery. Now, of the 2 of you that have site-wide disaster recovery, when was the last time you ran a DR test? Months ago? 6 months ago. So you're running it every 6 months, right? Say, for example, that's quite normal, right? And when you guys run your DR tests, how many times do they come up spot, absolutely perfect every time? It's never happened, right? It is running geo disaster recovery and having those kinds of capabilities is incredibly difficult in an on-premise world because it's very hard to manage all of the moving parts. What normally happens when a DR test happens is everybody realizes this is the gap of all the things that didn't work when we ran our DR test, and then they go and fix all of those things so that the list is drained so that the next time we run the DR test, we can pick out the things that we forgot from the last time, right? So it just is this continuing cycle of just trying to get to something that might work, but we know that actually doesn't based on previous performance. So what we try and do is make that a lot easier for you. And so we have the capability of enabling things like geo disaster recovery built into the service. So on a daily basis, we are shipping what we call, we use snapshots on the system. We create snapshots every 4 hours to support an 8-hour RPO. And we take one of those snapshots and we punt it over into the other region that's paired with your region. Okay? So if you're in Western Europe, we'll take one of those snapshots and stick it into Northern Europe, vice versa, the other way around. Okay? So that if there was anything to happen over here, you can restore that snapshot back up and you can be up and running on the other side. So notice I say this is geo-redundancy, i.e. the backup has been moved to the other side. This is not geo-replication, which would involve us having 2 live databases and running the transactions into both systems, right? So not geo-replication, geo-redundancy, okay? So you would still need to do the restore, but what we do is we assure you that you will have a copy of that database over on the other side, okay? And you can then use that backup to restore into any of the available regions. Now, obviously, we're going to enable a whole bunch of connectivity. So I'm going to I just put them up there so everybody knows that they're there and they're the options that you have available. Now, what I'm going to do is actually just drop into code just to kind of give you an example. And what I'm going to do is rather than do what we normally do, which is just show you this how to do this through the portal, right? I'm going to make the assumption that everybody here knows how to drive a user interface. And as we're at a SQL Saturday, I'm also going to make the assumption that most of you know some SQL. So I'm going to work on that basis, and we're going to move forward from there. So I'm just going to show you a couple of things, right? So this is the create database command, right? This is the full, complete end-to-end syntax for a create database command in T-SQL for SQL data warehouse. So what can you see about that is that there is no file placement. There is no file groups, nothing like that. All of that stuff is managed for you transparently down on the back end, right? The Contoso is the name of the database. There's a collation, addition, service objective, and max size. So the addition tells us that you want a SQL data warehouse, you don't want a SQL database, right? The service objective tells us what level of scale that you want. And then the max size is basically puts a cap. What we're doing is we're under the hood using premium storage as our primary storage. And we charge you based on a per terabyte consumption of that storage. So what we are also trying to do is to limit give you the opportunity to limit your consumption, right, of that storage capacity. Because if you can think about it, if you've got 2 enormous tables and someone was to do some kind of Cartesian product, right, into a new table, they could generate vast quantities of data, right? And that may not be desired, okay? So we enable you to control it somewhat crudely with a max size. So if I just execute that against system, one of the things we're going to do is you can just see that I'm just running that, and that's just running as a regular database command, and in about 5 minutes we'll have a database. But what we're going to do on the other side is I'm going to show you that we also enable you the ability to be able to see what's going on with that database. So you can see when I drop it or I alter it, what's going on, and you can see these are some of the previous things that I've run on the database commands. So I can see as I run that again. Oh, hang on a second. I lost my connection. Brilliant. That's just what you need. The perils of live demo. There you go. So he's now running that. That's the create database command that we're now tracking, and we're logging that. So you can actually put logic around looking at these factors. And this is a DMV that's relatively new, and it's something that's quite Azure specified, which is this sysdm operation status. So you can actually see events that are being logged into the system via this command. Okay, and you can also see that I'm tracking durations of events here. Okay, now that'll take a little while to run, so I'm also going to show you some other things whilst we wait. Now the next thing we're going to show you is the alter database command, and we can see that within the T-SQL I can connect via master and actually change my T-SQL, my compute power. Now, when I show you that, you'll see that actually that will happen, and it will be asynchronous, right? It will come back very, very quickly, even though it takes us 75 seconds. Why? Because when we do it, we're actually taking the databases offline to reallocate the compute to be able to reattach it, right? So bear in mind that when that's happening, you can't actually access the database directly, okay? So these commands are quite valid, valuable capabilities. Now, also, the other thing to bear in mind is that this process, your unit of compute that you run at, is based on an hourly charge, and it is the highest level that you have used within an hour. So, one of the reasons why I say this is because some people get kind of carried away a little bit with the slider, like the power control, right? You don't want to be doing this kind of like on a minute-by-minute thing, because actually you'll pay for the highest that you've used in an hour. So you tend to kind of optimize at that level of granularity, right? I'm going to run at DW2000 for 2 hours. I'm going to run at DW100 for 5 hours. I'm going to run at I'm going to pause it for the rest of the time, right? That sort of thing. You're not going to do, you know, for 5 minutes I'll be at 2000, for 10 minutes I'm going to be at 100, right? And then I'm going to pause it because you're still going to get charged for the 2000 for the hour.
A quick question, James. Is this perfectly balanced? I mean, I'm assuming it is. So however much compute you specify.
Yeah.
I mean, obviously this stuff has to run on real hardware
Yeah.
somewhere. You're not going to run into situations, or if you do, it's going to be very rare that you have idle CPU cores under the covers.
So what you can get, so when you get data skew in the system, so so if we step back a second and you think about the hash distribution, right?
You can get hot nodes.
You can get hot nodes on the, oh well, it's not so much the hot node, you can get a hot distribution, bear in mind separation of compute and storage, right? What you can get is the hot distribution, because let's say for example we had an eclectic retailer and all he decided he wanted to sell, right, was TVs and cans of Coke, right? Yeah. And that's the only two products he wanted to sell, and he had taken our industry model that was distributed by product. Yeah. So he's already got two problems, right? Yeah. The first problem is he's only loaded data into two buckets. Okay, so he's now got all the data in only 2 buckets. Now, if he's really unlucky, the hash has put the 2 values in the same bucket, right? Now, if he's moderately lucky, right, they're in 2 separate buckets. The next problem is he's got 2 products where the sales, no matter how hard he tries, are much more likely to favor the cans of Coke to the TVs. So he's going to have this massive skew. Now, what would happen in that scenario is, say we did our count, the count would run against all 60 distributions because we don't know where the data is, we just know it's distributed by a key, right? What would happen is we'll run the 60 queries, the 58 of them would finish really fast. The one that's only doing the TVs, that will finish quite quickly, obviously. And then the one that's got the cans of Coke, which would have all of the transactions, right, because it's just faster transactions, that guy is going to be the one that's going to have all the data. So he's going to take the longest. So you get this thing called skew. Now, skew can come in what I call primary and secondary skew. Okay, I'll talk to you later if you want to know about secondary skew. That's gets kind of complicated as a result of joins and stuff like that. But what you end up with is this kind of scenario. Okay.
So one more question: this uses column stores?
It does by default, yes.
Is there any facility to pre-sort the data before you actually create your column store?
We do not operate a sort key at the moment. Right? You can drop the data. You can force it. Right? By loading the data into a row store with a clustered key, right? Yeah. And then go from clustered key to column store. Right. Yeah, that's the forcing of a sort, right? Which is it's not part of an introducing to SQL data warehouse thing. That's the advanced bit, right? Is when you can start trying to optimize order into a column store, because a column store itself, even though it's called a cluster column store index, has no ordering on it at all, right? It's something of a misnomer. It just means it's the primary storage index. Okay, so happy to talk to you about that afterwards. Yeah, so you can see that create there, that took 106 seconds. Now what I can do is then run that modify and then run things like a loop over that modify using my new sysdm operation status to be able to poll for that. And then we'll look at that in a second. Now, the reason why I showed you that, you can see that one actually says it took a minute, but it's actually going to take about 75 seconds or so to run. And you can see that because I'm still waiting for that loop to finish, right? Now, the reason why I do it like this is because I want you to understand the core kind of concepts. The other thing to bear in mind is that when you connect to the master, you're actually connecting to the master, which is like a SQL database. So there are certain things that you can actually do in master that you can't do on SQL Data Warehouse. And one of those is the wait for command, right? We don't support wait for on the warehouse right now, but you can run it in the context of master because that's a SQL DB, right? So it's just a little a fun thing that you can kind of get. It helps get your head orientated around the sort of things that you can and can't do. Now, this is going to take a little time to run, so I'm going to show you what we're going to look at next, which is basically a data loading scenario. Okay. Now, in this, what we're going to do is start loading data via Polybase. Okay, and I'm going to show you how that actually works and what the basic mechanics of that are. Okay. What we need to do when we create a Polybase is we basically create a schema, because I'm just a bit schema obsessed. Then we create a master key and a database scope credential. And that basically gives us the permissions to read from blob storage, right? It gives us the access. So we have a private key. And then we basically create something called an external data source. The external data source is telling us where is our blob storage. So here you can see I have a storage storage account called JRJ Contoso DWSACC, which is Contoso Data Warehouse storage account, right? And that's my blob storage account. And in there I have a container called Contoso Retail Data Warehouse. So this tells me where the data is, and there you can see I'm applying that credential to the data. Now, if I'm using a public container, I just don't even need to mention that. Now, that data is going to be in a delimited file, and so in this case, I need to tell it how to parse the file, right? What the field delimiter is, what the string delimiter is, date format, use type default. Okay, they're the basic options, and I can also have a different one that I use for data compression, i.e. I can read compressed data files. Now, the thing I want you to make sure you understand is this thing here, right? It says gzip codec, right? Basically, that is gzip compression, not WinZip compression, right? Very different things, okay? So we support a gzip compression, not a WinZip compression, but you can load from compressed data into SQL Data Warehouse. Now, once you've done that, you can then run in data by creating a mapping using essentially a table format, right? So you can see here, all we do is we call it an external table because the data is held externally. There's no data in the table. The table itself is empty, but the data is held externally. So it's decoupled from the storage. So we're going to create this. And all we're doing is creating a mapping at this point. And it basically says, within the container, show me the path to the actual file we want to load, and then data source and file format. Okay? Now, just to go back to our alter statement, you can see that it is finished, that we're now running at DW400, and that took 1 minute 16 seconds, i.e. 75 seconds, and then if we run up here, run our DM operation status, we can see that there is our alter statement, right? So we can see that our actions are monitored and logged. So now what I'm going to do is I'm actually going to create 4 external tables off that data: uncompressed 1, uncompressed 60, compressed 1, and compressed 60. So I've got the same data laid out in different ways, right? All the data in one file, uncompressed. All the data in one file, compressed. All the data in 60 files, uncompressed. And all the data in 60 compressed files. So I'm just going to connect quickly as a final thing, run that on, and then I'm going to quickly show you how to load this data. So those commands, I'm just loading them all in one go. And whilst that's happening, I'm just going to make the connections on this other. I must have a second one in there somewhere. Ah, there it is. Apologies. So. Oh, I put a go in it, that's why. So you can see over here that I now have a whole bunch of objects inside my SQL Data Warehouse database. So hopefully there's a couple of things I want you to recognize here. First of all, the Contoso Retail Data Warehouse is just a single database. Okay? And in there, I now have these 4 external tables and our file formats. So to load that data, we use something called a CTAS operation, or create table as select. And here I'm going to run that data in with a single command. And I'll first create the temporary table, the schema for that. And we can run that data in. Now, when I'm running that data in, one of the things that you have to be there for is looking at how the data is accessed. Even though the data is coming in a single file, we actually split that file into 500 megabyte chunks, 512 megabyte chunks. So we're actually able to read into offsets of that file. Okay? So we're able to parallelize even with a single file into using Polybase. Now, that doesn't always happen. Unfortunately, I've run out of time, but that doesn't always happen if you have compressed data. So when you have compressed data, you want to actually split the data across multiple files to make sure you get the full parallelism in the system. Now, I have got this built as a demo up online with the full thing, so you're more than welcome to look at that yourselves. I just want to thank everybody for their time today. Oh, there he goes. He's run now. And thank the organizers and the helpers for making this day possible. I do want to stress that nobody actually helping to do this event, actually helper or organizer, is paid in any way, or speaker, to make this day happen. And so when you see someone who is clearly involved in the event, you please take a moment and thank them for their support, because without them, none of this happens. And so they are very, very greatly appreciated. So here's those links that I promised you. You can take a picture of that or make the slides available afterwards. Other than that, thank you very much for your time. And I look forward to hearing about your SQL DW adventures. I'll be around for most of the rest of the day. Yeah, that's it. Thank you very much.